You know that almost magical speed when you look something up online? Or like how a dictionary app just snaps to the word you need. That speed, well, it often comes down to some pretty clever data structures.
And right at the core of those structures, sort of the engine driving that speed, is something called a hash algorithm.
Right. And that's what we're digging into today. We've got these fantastic notes and excerpts you shared, focusing specifically on how these algorithms tick and why they're built the way they are.
Exactly. So the plan is to really unpack those notes, get a solid handle on the core ideas behind hash algorithms.
And figure out what makes one good, right? Because it's not just abstract theory, is it? This stuff impacts everything from how fast your databases run to keeping your passwords safe online. We want you to really get this so it sticks.
Absolutely. It's very practical. At its heart, a hash algorithm takes some input data, could be anything, a word, a username, we call it a key, does some calculation on it and spits out a number. That number is the hash value.
Okay, so input, calculation, Vine, number, output.
Yeah. And in something like a hash table, which is a common data structure using this, that hash value is then often used to figure out where to store or find the data in an array. Usually you take the hash value modulo the size of the array.
Ah, right, the modulo operator.
Yeah.
So the basic idea is index equals hash key percent capacity. That hash key part is the function doing the core work of getting you to an index quickly.
That's the one. But here's the catch. The fundamental problem that hashing introduces, and something your source material really emphasizes, what if two different keys go through the hash function?
And end up with the same hash value, or the same index after the modulo.
Precisely. That's called a hash collision.
The infamous collision. Sounds like the big villain for hash tables.
It really is. Collisions mean multiple keys are trying to occupy the same storage spot. Now, data structures have ways to deal with this, strategies like chaining.
Or you just make a little list at that spot for all the colliding items.
Yeah, or open addressing where you look for the next empty slot nearby. But while you can handle collisions, how often they happen in the first place, that comes down to how good your hash algorithm is.
And the notes show just how critical that is. If you get lots of collisions because of a poor hash function, say in that chaining example, suddenly all your keys pile up in one or two lists.
Right. And your supposedly super fast lookup, which should ideally be almost instantaneous, to call it O1, just degrades completely.
You end up having to just search through that whole long list at that one index.
Exactly. And in the absolute worst case, if a truly terrible hash function dumps every single key into the same bucket, well, you're back to searching through everything, item by item. That's OMASL, linear search.
Which totally defeats the whole point of using a hash table for speed in the first place.
Completely. So minimizing those collisions is absolutely paramount for performance.
Okay, so job number one for a hash algorithm used in a hash table. Avoid collisions as much as possible. What does it need to do well? What makes a good hash function according to the sources?
Well, the notes lay out a few essentials. First, and this is absolutely non-negotiable for finding things again, is determinism.
Meaning?
Meaning, if you put the same key in, you must get the exact same hash value out every single time. No exceptions.
Makes sense. Otherwise, you'd store something and might never find it again. Like
Yeah.
a faulty calculator button.
Exactly. Second, high efficiency. The calculation itself, computing the hash, has to be fast. If hashing takes ages, it eats into the time you save by jumping straight to the index.
Got it. The whole process needs speed.
And third, this is the big one for avoiding collisions in hash tables, uniform distribution. Ideally, the hash values produced should be spread out as evenly, as randomly as possible across the whole range of potential outputs.
So when you do that modulo operation to get the table index, the keys get scattered nicely across all the available buckets.
That's the goal. Uniform distribution directly reduces the chances of those collisions happening.
Okay, so determinism, high efficiency, uniform distribution. Those are the targets for hash table performance. But the sources make it clear hashing isn't just for hash tables. It's huge in security, too.
Oh, absolutely. Your materials highlight two massive real-world uses: password storage and data integrity checks. Let's take passwords. When you create an account somewhere, the system shouldn't store your actual password.
Right, that would be terrible if they got hacked.
Exactly. Instead, they run your chosen password through a hash algorithm and store the resulting hash value.
And then when I log in later, they hash the password I type in that moment
Uh-huh.
and just compare that new hash with the one they stored. If they match, I'm in.
Precisely. The actual password is never stored, just the hash. It's a fundamental security practice.
And data integrity, how does that work?
Imagine downloading a big file, like an operating system image or some software. Often, the download site will also list a hash value for that file. You might see labels like MD5 or SHA-256.
Oh yeah, I've seen those checksums.
Right. So once you've downloaded the file, you can run a tool on your computer to calculate the hash of the file you received.
And if my calculated hash matches the one the website provided.
You can be pretty confident the file wasn't corrupted during the download and, importantly, that it hasn't been tampered with by someone malicious since the original hash was created.
That's clever.
Yeah.
So for these security applications, the hash algorithm needs more than just speed and spreading things out, right?
Yeah.
It needs to be, well, tougher.
Much tougher. The sources list these extra crucial security properties.
Okay.
First, unidirectionality, or being one way. It must be practically impossible. Computationally infeasible is the term, to take a hash output and work backward to figure out the original input data.
You can't reverse engineer the password from its hash.
Exactly. Second, collision resistance. Now, this sounds like uniform distribution, but it's subtly different and much stronger. It has to be incredibly hard for anyone, even someone deliberately trying, to find two different inputs that produce the exact same hash output.
Okay, hold on. You specifically said collision resistance is different from uniform distribution. This feels important. One of those key distinctions the notes are making. Can you unpack that with the example they gave?
Yes, this is a really critical point. Your source material hammers home. Uniform distribution is about how well typical inputs get spread out. Collision resistance is about how hard it is to intentionally engineer a collision. Let's use that simple key percent 100 example from the notes.
Okay. Hashing is just take the number modulo 100.
Right. Now, if your incoming keys were, say, perfectly random numbers, the results of key percent 100 might actually be spread pretty evenly across the numbers 0 to 99. So you might argue it has decent uniform distribution for random data.
Seems okay for spreading keys in a hash table, maybe?
Maybe for basic speed, but it's terrible for collision resistance, which is what you need for security. Why? Because finding two different keys that give the same result is trivial.
How so?
Any two numbers that end in the same two digits will collide. 101 hashes to 1. 201 hashes to 1. Collision. 57 hashes to 57. 1157 hashes to 57. Another collision. You can find collisions instantly, effortlessly.
Ah, I see it now. So uniform distribution is about spreading out average inputs, but collision resistance is about making it hard to deliberately find any two inputs that collide. The purport 100 thing might spread random stuff okay, but it offers zero resistance if someone wants to cause the collision.
Exactly that distinction. For hash tables, good uniform distribution is usually enough to minimize accidental collisions and keep things fast. For security uses like passwords or integrity checks, you absolutely need strong collision resistance to prevent malicious attacks.
Got it. So how do people actually design algorithms to get these properties? The notes mention some simple approaches, but then really zoom in on using prime numbers.
Right, the very simple ideas like just adding up character values or XORing them or rotating bits. Your sources call these fragile. They have known weaknesses. For instance, just adding or XORing values means the order doesn't matter. Cat and act would hash to the same value, which is often undesirable.
But many of these simple methods, and even more complex ones, often end with a modulo operation. And the notes make a really big point about using a large prime number for that modulo, like 100,000,000,000,000,000,000 instead of a composite number. Why is prime better? This seems like another one of those deep insights.
It is a key technique, especially for optimizing distribution. The choice of the number you take the modulo with the modulus significantly affects how evenly the hash values are spread, particularly if the input keys themselves have some kind of pattern, which real-world data often does. Let's walk through that example from the sources. It makes it really clear.
Okay, lay it on me.
Let's say you use a composite number, one with factors like 9. 9 is divisible by 3. Now imagine your input keys aren't random, but they follow a pattern related to 3. Like maybe they're just multiples of 3, 0, 3, 6, 9, 12, 15, and so on.
Okay, P's are 0, 3, 6, 9, 12.
Now calculate the hash using keeper C9. What do you get?
Let's see. 0%, 9 is 0.3%, 9 is 6, 9%, 9 is 0, 0.12%, 9 is 3, 15%, 9 is 6. Oh,
right.
It's repeating. 0, 3, 6, 0, 3, 6.
Exactly. Even though the input keys are increasing, the hash values are stuck cycling through just 0, 3, and 6. They're heavily clumped. If you had a hash table with 9 buckets, all these keys would pile up in only buckets 0, 3, and 6.
That's terrible distribution. The pattern in the keys, multiples of 3, interacted badly with the factors of the modulus, 9 being divisible by 3.
Precisely. Now let's switch the modulus to a prime number, say 13. Use the same input keys, 0, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33.
Okay, calculating key percent 13, 0, 3, 6, 9, 12, and 15% 13 is 2, 18% 13 is 5, 21% 13 is 8, 24% 13 is 11, 30% 13 is 4, 33% 13 is 7.
See the difference? The results, 0, 3, 6, 9, 12, 2, 5, 8, 11, 1, 4, 7, are spread all over the range from 0 to 12.
That's dramatically better. They're hitting almost all the possible values very quickly.
Because 13 is prime, it doesn't share factors with potential periodic patterns in the input keys in the same way a composite number like 9 does. This helps to break up those patterns and distribute the results much more uniformly across the entire range of possible outputs 0 to modulus 1.
So using a prime modulus is a practical trick to boost that uniform distribution, making collisions less likely, especially when your input data isn't perfectly random, which it usually isn't.
Exactly. It's a standard technique for improving simple hash functions where good distribution is the main aim. But like we said, these simple methods aren't usually good enough for security.
Right, because they lack things like strong collision resistance or that one-way property. That's where the heavy hitters come in the standard cryptographic hash functions like MD5, SHA-1, SHA-2, SHA-3.
Yes, these are specifically designed for security. They take an input of essentially any length, could be a single byte, could be terabytes of data, and produce a fixed size output, a digest or hash value that meets those tough security requirements. Your sources give a nice history of their development.
It really does look like a cat and mouse game or an arms race.
It kind of is. MD5 came out in 92. SHA-1 in 95. They were the standards for a while. But then researchers, cryptanalysts started finding weaknesses.
Finding ways to break that collision resistance property, like actually finding two different inputs that hashed to the same output much faster than just guessing randomly.
Exactly. Practical collision attacks have been demonstrated for both MD5 and SHA-1. So the sources correctly state they're now considered broken for security-sensitive uses. You might still see MD5 for a basic file integrity check sometimes where the risk is low, but definitely not for passwords or digital signatures anymore.
So they were retired from the front lines. What took their place for serious security?
That would be the SHA-2 family, introduced around 2002. It includes algorithms like SHA-256 and SHA-512. The number indicates the length of the hash output in bits.
Longer hash, generally harder to break.
Generally, yes. More bits means a vastly larger output space, making collisions statistically rarer and brute force attacks harder. And crucially, the internal design of SHA-2 is much stronger. Your sources note that, as of now, no practical attacks against SHA-2 have been publicly confirmed. It's the workhorse standard today for things like blockchain transaction verification, SSL/TLS certificates, digital signatures, lots of critical stuff.
Okay, SHA-2 is the current champ, but then there's also SHA-3.
Yes, the SHA-3 was standardized later, around 2008, after a public competition run by NIST. It's based on a completely different internal structure called a sponge construction, unlike the Merkle-Bamgord structure used in MD5, SHA-1, and SHA-2.
Why a different structure?
Partly as a backup, in case unforeseen weaknesses were ever found in SHA-2. Also, SHA-3 was designed with aims like potentially better performance in certain hardware implementations and maybe simpler analysis. It's considered highly secure, offers various output lengths just like SHA-2.
But the notes say it's maybe less widely used than SHA-2 right now.
That seems to be the case currently.
Yeah.
SHA-2 had a head start and is deeply embedded. SHA-3 is secure and available, but maybe hasn't seen the same level of universal adoption yet. The key takeaway is that we have these robust, standardized options designed specifically for high security.
Yeah, the table in the notes summarizing them: release year, output size, collision frequency moving from frequent for MD5 SHA-1 to rare for SHA-23, security level applications. It paints a clear picture of progress and the need for ongoing vigilance.
It definitely shows it's an evolving field. You can't just design one algorithm and assume it's good forever.
Okay, let's shift gears slightly. How does all this hashing stuff actually appear when you or I sit down to write code? The sources mention languages have built-in hashing capabilities.
They do. Most mainstream languages provide some kind of built-in hash function. You know, Python has hash, Java has hash code. These functions are what the language uses behind the scenes when you use its built-in hash table structures like Python dictionaries, dict, or Java hash map.
And these built-in functions know how to handle different kinds of data, like numbers, text, etc.
Generally, yes. The sources give examples. Simple integers might just hash to their own value. Booleans, too. Floating point numbers need a more careful approach to handle potential representation issues. Strings usually involve iterating over the characters and combining their values in some way. Tuples, which are like immutable lists, typically hash based on the hashes of their contents.
What about objects? Like custom classes we define.
By default, in many languages like Python or Java, an object's hash code is often based on its identity, essentially its memory location. This guarantees that a specific object instance always has the same hash code throughout its life.
But what if I want two objects that have the same data inside them to be treated as equivalent keys in a hash map?
Then you typically need to override the default hashing behavior. You'd write your own hash code in Java, or hash in Python method, for your class that calculates a hash based on the object's content, the values of its important fields, rather than its memory address. You also need to override the equality comparison method, equals or EQ, consistently.
Okay, that makes sense. But the sources stress a really, really important rule here. Only immutable objects should be used as keys in hash tables. Why is immutability so crucial? This seems like a pitfall programmers need to avoid.
This is absolutely fundamental. Let's walk through why immutable objects are a problem. A hash table relies on the key's hash value to determine where to store the associated value. That hash value is calculated once when you insert the key value pair.
Okay, so I put my key in, calculate its hash, find the bucket, store the value.
Right. Now imagine your key is a mutable object like a Python list. My list equals 1, 2. And let's say its hash value is computed based on its contents, 1 and 2. You use this list as a key.
Got it. Might have in my list some data.
Exactly. Now later in your code, because lists are mutable, you modify it in place. MyList.append 3. So the object that's acting as your key now contains 1, 2, 3.
No.
Oh, is right. If you now try to look up mydictmymylist, what happens? The hash function runs again on the current contents, 1, 2, 3. This will almost certainly produce a different hash value than the original hash based on 1, 2.
So the dictionary looks in a completely different bucket. It won't find the data stored under the original hash.
Correct. The link is broken. The key, in essence, changed its identity from the perspective of the hash table because its hash value changed.
Right.
You can no longer reliably retrieve the data using that key object. It might even mess up the internal state of the hash table.
That's why you need immutable keys like numbers, strings, or tuples. Their contents can't change after creation, so their hash value, if based on content, remains constant for their entire lifetime. They provide a stable address.
Exactly. Stability is key for keys.
And one last detail from the notes, that interesting bit about Python adding a random salt to string hashing each time it starts up. What's that about?
Yes. That's a specific defense mechanism against something called a hash denial of service, or hash DOS attack.
How does that work?
Well, if an attacker knows the exact algorithm a web server, say, is using to hash strings, perhaps for keys in a dictionary that stores session data or request parameters, and if that algorithm is purely deterministic in the traditional sense.
Same string input always gives the same hash output.
Right. Then the attacker could potentially pre-calculate a large number of different strings that they know will all hash to the same value, causing deliberate collisions.
Like finding lots of strings that all end up in bucket number 5, for example.
Precisely. If the attacker then sends a request containing many of these collision-causing strings as keys, the server's hash table performance for those keys plummets from O1 towards ON because it has to search through long chains.
Tying up the server's CPU, processing these deliberately inefficient lookups. A denial of service.
Exactly. By adding a random secret salt value to the string hashing process each time the Python process starts, the hash value for any given string becomes unpredictable to an outside attacker. They don't know the salt, so they can't craft inputs guaranteed to collide. It effectively randomizes the hash outputs relative to the inputs for that specific running process.
That's a clever practical defense against a specific attack vector. It really shows how these algorithm details matter in the real world.
It really does. From basic data structure speed to sophisticated security defenses, hash algorithms are working away under the hood.
So let's try and wrap this up. Looking back at this deep dive, drawing from your sources, what are the core things we, and you, the listener, should really take away about hash algorithms?
I think first is just understanding their dual role. They're crucial for performance in data structures like hash tables, where the goal is fast lookups, achieved primarily through good uniform distribution to minimize accidental collisions.
Right. And second, they're absolutely fundamental for security protecting passwords, ensuring data integrity where the demands are much higher. You need those stronger properties like being one-way and, crucially, collision-resistant to thwart deliberate attacks.
We also saw that designing these algorithms isn't trivial. There are techniques, like using prime moduli, to improve distribution in simpler cases. And for security, there's this ongoing evolution of standards, from MD5 and SHA-1, which were eventually broken, to the robust SHA-2 and the alternative design of SHA-3 we rely on today.
And finally, we saw how these concepts directly impact programming, like the critical rule about using only immutable objects as hash keys, and even security features like Python's salted hashing to prevent specific attacks like hash DOS. Understanding this stuff really gives you a much better appreciation for how so many digital systems work efficiently and securely.
Absolutely. They're foundational building blocks. Which leads us, I think, to a final thought for you to mull over. We've talked about this evolution, MD5 to SHA-1 to SHA-2 to SHA-3. It's this constant cycle. Researchers design algorithms they believe are secure based on current knowledge. Then other researchers or attackers probe them for weaknesses, sometimes finding breaks years later, forcing the development of new, stronger algorithms. This perpetual push-pull, this arms race between code makers and code breakers in the realm of hashing. What does this ongoing need for ever stronger cryptographic hashing really tell us about the fundamental nature of information security itself in our digital world? Is perfect, lasting security ever truly achievable, or is it always a moving target?